C# and AI Masterclass by Edgar Milvis Volume 4, Chapter 3. Let's discuss Chapter 3, Task versus ValueTask, Optimizing Memory in Hot Loops. Now, let's explore theoretical foundations. In the high-stakes domain of asynchronous programming, particularly within the latency-sensitive loops of AI pipelines, the allocation of memory is not merely a technical detail, it is the primary bottleneck. When processing thousands of tokens from a large language model, LLM, in a streaming fashion, every microsecond and every byte allocated on the heap contributes to the pressure on the garbage collector, GC. If the GC pauses execution to clean up unused objects, the illusion of real-time streaming shatters, resulting in jittery user experiences and inefficient resource utilization. To understand the optimization of memory in these hot loops, we must first dissect the fundamental building blocks of asynchronous state machines in C#, task and ValueTask. While they appear similar on the surface, their memory profiles and usage patterns are diametrically opposed. This distinction is critical when designing systems that require both high throughput and low latency, such as tokenizers, vectorizers, or inference engines. Now, let's talk about the anatomy of asynchronous overhead. In modern C#, asynchronous methods are transformed by the compiler into state machines. When an async method is invoked, it does not immediately execute. Instead, the compiler generates a struct, or class, that tracks the current state of execution, e.g., which await point it is currently paused at, local variables, and the context. This state machine is the heart of async execution. However, the return type determines how this state machine is exposed to the caller and how memory is managed. Now, let's talk about the heavyweight, task and task allocation. A task is a reference type, a class. It represents a promise of a future result. When you return a task from an asynchronous method, you are returning a reference to an object allocated on the managed heap. Consider a method that checks if a model is ready. Here, we're defining a public asynchronous method named IsModelReadyAsync. This method is designed to check the readiness of a hypothetical AI model. The async keyword is crucial, it signals to the C# compiler that this method contains awaitable operations and will return a task or task it. In this case, it returns task bool, indicating that the operation will eventually yield a Boolean result. This pattern is fundamental for non-blocking I/O operations, which are essential for maintaining responsiveness in modern applications, especially in web servers or UI-heavy applications. If we didn't use async, any I/O operation would block the calling thread, leading to performance bottlenecks and poor user experience. Look at lines 3 to 6. Inside our IsModelReadyAsync method, we're simulating an I/O bound operation using await task, delay, 10. This isn't a real network call or disk access, but it effectively mimics one. The await keyword is the magic here, it tells the runtime that the current method can pause its execution at this point and yield control back to the caller. While the task, delay is running, simulating work, the thread that called IsModelReadyAsync is free to do other things, preventing it from blocking. Once the delay is over, the method resumes from where it left off. Finally, return true, indicates that our simulated model is always ready. This simple simulation helps us focus on the asynchronous pattern without needing a complex backend dependency. In a real-world scenario, this task, delay would be replaced by an actual asynchronous call to a database, an external API, or a computationally intensive model loading process. Every time IsModelReadyAsync is called, the following occurs. 1. Heap allocation, a task bool object is allocated on the heap. 2. State machine allocation. The compiler-generated state machine, a class, because it captures the async method's context, is also allocated on the heap. 3. Continuation overhead. When the await completes, a continuation delegate is allocated to schedule the rest of the method. In a typical application, this overhead is negligible. But in an AI pipeline, imagine a loop processing a stream of 4,000 tokens. Here, we're iterating through a stream of tokens, and for each token, we're asynchronously processing it using ProcessTokenAsync. Notice the await keyword within the loop. This means that each iteration of the loop will pause until ProcessTokenAsync completes for the current token before moving to the next. This approach guarantees sequential processing, which is crucial when the order of operations matters, for example, if ProcessTokenAsync modifies a shared state or if the output of one token's processing is an input for the next. However, it also implies that the total time taken will be the sum of the processing times for all tokens, which might not be optimal for independent operations. If ProcessTokenAsync returns a task, this loop allocates 4,000 objects on the heap. In a high-throughput scenario, e.g., 100 requests per second, this results in millions of allocations per second. The GC must run frequently, Gen 0 collections, to reclaim this memory, causing stop-the-world pauses that disrupt the smooth flow of data. Let's discuss the lightweight, ValueTask and stack allocation. ValueTask, introduced in C# 7.0 and significantly optimized in .NET Core 2.1 and later, is a struct. It is a value type, meaning it can be allocated on the stack rather than the heap. ValueTask T is a discriminated union that can hold one of two things: 1, a T result, if the operation completes synchronously. 2. A task T a result, if the operation completes asynchronously. This distinction is the key to memory optimization. If the path of execution leads to a synchronous completion, e.g., data is already cached, or a lock was acquired immediately, ValueTask wraps the result directly in the struct on the stack. No heap allocation occurs. Here, we're defining a method called IsModelReadyAsync that returns a ValueTask bool. This is a crucial architectural choice for performance optimization, especially in high-throughput scenarios. Instead of always returning a task bool, which is a reference type and thus incurs heap allocations, ValueTask T allows us to return a value type when the operation can complete synchronously. This significantly reduces garbage collection pressure and improves overall responsiveness, which is vital for an AI pipeline where latency is often critical. We're essentially trying to avoid unnecessary object allocations when the answer is already known. In the context of an AI pipeline, ValueTask is the scalpel used to carve away unnecessary allocations. When processing tokens, if a token is found in a local cache, a common optimization in tokenizers, the method returns immediately without touching the heap. Moving on to the hot loop in AI pipelines. To visualize where this matters, consider the architecture of a streaming LLM response. The pipeline typically looks like this: 1. Inference engine generates tokens one by one. 2. Tokenizer encodes/decodes tokens, often synchronous or extremely fast. 3. Network stream sends tokens to the client, asynchronous I/O. The hot loop is the innermost cycle of this pipeline. It runs thousands of times per request. The hot loop is the innermost cycle of the pipeline, running thousands of times per request to process data with maximum efficiency. In the diagram above, the left side, synchronous path, represents the ideal scenario for ValueTask. The right side, asynchronous path, represents the fallback to task. Moving on to the mechanics of ValueTask and ValueTask T. ValueTask is not magic, it is a carefully engineered struct. Its internal structure looks roughly like this, conceptually. Here, we're looking at the definition of the ValueTask T result struct. This is a crucial type in modern asynchronous programming in .NET, especially when performance and memory allocation are paramount. Unlike task T result, which is always a reference type and thus involves heap allocations, ValueTask T result is a struct. This means it can often be allocated on the stack, reducing garbage collection pressure. The core idea is to provide a unified way to represent an operation that might complete synchronously or might complete asynchronously. This design is particularly beneficial in scenarios where operations frequently complete synchronously, allowing us to avoid the overhead of allocating a task object for each synchronous completion. We'll see how this plays out in its internal structure. Notice the two primary fields within ValueTask T result and _task. This dual field approach is the heart of its efficiency. The _result field, a T result, is used when the operation completes synchronously. If the result is immediately available, ValueTask can simply store it here. This is incredibly efficient as no task object needs to be created, and no heap allocation occurs. Conversely, if the operation needs to truly execute asynchronously, then a task T result object is created and stored in the _task field. This clever design allows ValueTask to switch between a lightweight synchronous representation and a more traditional asynchronous task representation as needed. The comment about a token for pooled tasks hints at even further optimizations, where ValueTask can sometimes leverage pooled ValueTask source objects to manage asynchronous operations without allocating new task objects every time, further reducing memory churn. This is a deep optimization for high-performance scenarios. When you await a ValueTask, the compiler generates a state machine that checks if the task is completed. If _result is set, it returns immediately. If _task is set, it awaits the task as usual. Let's discuss the critical constraint, hot path usage. There is a strict rule when using ValueTask: you can only await it once. Because ValueTask may wrap a pooled task, be it task.completed task or a custom pool, awaiting it twice can lead to race conditions where the underlying task is returned to the pool and reused before the second await completes, causing unpredictable behavior. This makes ValueTask ideal for hot paths, methods that are called frequently, complete quickly, often synchronously, and are not designed to be awaited multiple times, e.g., by multiple listeners. Turning our attention to real-world analogy, the library and the librarian. To understand the memory implications, imagine a library, the heap, and a librarian, the garbage collector. The task approach, the book request. You are a researcher, the CPU, needing facts, the result. Every time you need a fact, you write a formal request slip, allocate a task object, and hand it to the librarian. The librarian files the slip and eventually brings you the book. Once you are done with the fact, you throw the request slip in the trash. If you need 4,000 facts, you generate 4,000 slips. The librarian, GC, must constantly empty the trash can, collect Gen 0 garbage, to keep the desk clean. This is slow and labor-intensive. The ValueTask approach, the sticky note. You are a researcher sitting at a desk with a notepad, the stack. You need a fact that is likely written on a sticky note on your monitor, synchronous completion/cache hit. You glance at it and write it down immediately. No request slip is used. Only when the fact isn't on the sticky note, asynchronous completion/cache miss, do you write a formal request slip, allocate a task. This drastically reduces the paper waste, memory allocations, and the librarian's workload, GC pressure. Now, let's explore integration with previous concepts, async streams. This concept builds directly upon Book 3, Chapter 2, Async enumerable and streaming, where we discussed how to yield data asynchronously. When implementing async enumerable T for streaming LLM tokens, the MoveNextAsync method returns a ValueTask bool. Why? Because in a high-frequency loop iterating over a stream. Here, we're observing a powerful C number 8 feature, a wait for each. This construct is specifically designed for asynchronously iterating over async enumerable T sequences. Instead of blocking the thread while waiting for the next item in the stream, a wait for each allows the current method to yield control back to the caller, freeing up the thread to do other work. This is absolutely critical in high-performance, I/O-bound applications, such as those interacting with large language models, LLMs, over network streams. If we were to use a synchronous for each loop here, the entire thread would be blocked until the LLM stream completed, leading to poor responsiveness and scalability, especially under heavy load. Imagine a web server trying to handle hundreds of concurrent requests. Blocking threads would quickly exhaust the thread pool and bring the server to a halt. By using a wait for each, we ensure that our application remains highly concurrent and responsive, making efficient use of system resources. The MoveNextAsync call is the heartbeat of the loop. If the buffer has a token ready, synchronous, it returns true immediately via ValueTask. If it needs to wait for the network, asynchronous, it returns a task. Using ValueTask here ensures that the loop itself does not induce heap allocations during the synchronous processing of buffered tokens, which is the majority of the time in a buffered stream. Let's discuss architectural implications for AI systems. When designing AI pipelines, the choice between task and ValueTask dictates the scalability of the system. 1. Tokenizer optimization. Tokenizers often involve dictionary lookups and string manipulations. If a tokenizer is implemented to check a local LRU cache before performing the heavy encoding, the cache hit path should return ValueTask string. This ensures that the most common operation, retrieving a cached token ID, incurs zero GC pressure. 2. Vector database lookups. When retrieving vector embeddings for a prompt, the data might be cached in memory. A method getEmbeddingAsync returning ValueTask float allows the system to return the cached array synchronously. Only when the cache misses does it switch to the asynchronous database fetch, returning a task float. 3. Batching inference requests. In a batch processing loop, where the system waits for a batch of tokens to fill up before sending them to the GPU, the wait time is often deterministic. If the wait time is 0, the batch is already full, the method can return a ValueTask representing immediate readiness. This allows the loop to spin faster without allocating objects for every iteration. Now, let's talk about the hidden cost, the task fallback. It is vital to understand that ValueTask is not a silver bullet. If the operation always goes down the asynchronous path, e.g., every call requires a network round trip, ValueTask actually introduces more overhead than task. Why? 1. Struct copying. ValueTask is a struct. Returning it involves copying its fields, 2 references, _result and _task. This is a tiny cost, but non-zero. 2. Double indirection. If ValueTask wraps a task, the await keyword has to unwrap the struct to get the task, then await the task. This is slightly more work than directly awaiting a task. Therefore, ValueTask is strictly for optimistic scenarios where synchronous completion is the dominant path. In an AI pipeline, this optimism is usually justified because in-memory caches and pre-processed data are prevalent. Turning our attention to theoretical foundations. The theoretical foundation of task versus value task rests on the trade-off between abstraction and allocation. Task provides a robust, reference-type abstraction for concurrency. It is safe to share, safe to await multiple times, and flexible. However, it lives on the heap, and the GC must eventually clean it up. ValueTask provides a lightweight, value-type optimization for the specific case where an asynchronous operation completes synchronously. It minimizes heap allocations but imposes constraints, single await, and requires careful architectural planning. In the context of building high-performance AI applications, mastering this distinction allows the developer to flatten the latency curve. By ensuring that the happy path, cache hits, immediate readiness, generates zero garbage, the application maintains a steady throughput, ensuring that the user perceives the AI's response as instantaneous and fluid. Turning our attention to basic code example. Here is a basic code example demonstrating the difference between task and value task in a hot loop scenario, specifically tailored for processing streaming tokens from an LLM. We begin by importing necessary namespaces. System provides fundamental types and base classes. System, collections, generic is crucial for working with collections like dictionary, which we'll use for our cache. And system, threading, tasks is absolutely essential for asynchronous programming in C#, providing the task and value task types that are the core of this example. Without these, we couldn't implement our asynchronous processing strategies. Here, we define our LLM token processor class, which will encapsulate our token processing logic. Inside, we create a static, read-only dictionary called _embedding cache. This is a mock database, simulating a real-world cache for token embeddings. Notice the static keyword. This means the cache is shared across all instances of LLM token processor, though in this console app, there's only one logical context. The read-only keyword ensures that the dictionary instance itself cannot be reassigned after initialization, though its contents can be modified. This cache is critical for demonstrating the performance benefits of ValueTask when dealing with frequently accessed, synchronously available data, like cached embeddings. In a production system, this would likely be a distributed, high-performance cache like Redis or Memcached, not an in-memory dictionary. The main method is the entry point of our application. It's marked async task because it will perform asynchronous operations. We start by printing a header to the console. Then, at line 22, we define an array of tokens that simulate a stream of data from a large language model, LLM. In a real-world scenario, this would likely be an async enumerable string to handle potentially infinite streams of tokens efficiently. At line 25, we capture the initial memory usage using gc.getTotalMemory, true. This is a crucial step for accurately measuring the memory impact of our different asynchronous processing strategies. We're interested in the heap allocations, and garbage collection statistics will help us quantify that. We now introduce the first processing strategy, using task. This is the standard, most common way to handle asynchronous operations in C#. We print a descriptive header and then call processTokens with task, awaiting its completion. After it finishes, we again measure the total memory used. The difference between memory after task and initial memory will give us an indication of the heap allocations made by the task-based approach. This strategy is robust and widely used, but as we'll see, it can introduce overhead in specific, hot path scenarios where operations frequently complete synchronously. Before moving to the next strategy, we perform a critical step, forcing garbage collection at lines 35 to 37. GC, collect, and GC.wait for pending finalizers, are used to ensure that any memory allocated by the previous task-based processing is reclaimed by the garbage collector. This provides a cleaner slate for measuring the memory impact of the ValueTask strategy. Without this explicit garbage collection, the memory measurements for ValueTask would be skewed by the allocations from the task strategy. Then, at line 39, we capture the memory again, and at line 42, we execute processTokens with ValueTask. Finally, at lines 45 to 46, we measure the memory after the ValueTask processing and report the difference. This direct comparison will highlight the memory efficiency benefits of ValueTask. This method, processTokens with task, demonstrates the standard asynchronous pattern using task. Notice at line 59, we await getEmbedding as task async, token. The key takeaway here is that await a task always involves a heap allocation for the task object itself, even if the underlying operation completes synchronously, e.g., a cache hit. This is because task is a reference type. For a small number of operations, this overhead is negligible. However, in scenarios with very frequent, synchronous asynchronous operations, like processing a high volume of cached LLM tokens, these repeated allocations can lead to increased garbage collection pressure and reduced performance. The if embedding equals null block at line 62 is just simulating some work being done with the embedding, indicating that a successful retrieval occurred. Now we move to process tokens with ValueTask, which showcases the optimized approach using ValueTask. The structure looks very similar to the task version, but the crucial difference lies in what getEmbeddingAsValueTaskAsync returns. At line 80, we await a ValueTask. The primary benefit of ValueTask is its ability to avoid heap allocations when the awaited operation completes synchronously. If the result is immediately available, e.g., from our cache, ValueTask can return a struct directly, which is allocated on the stack. This significantly reduces pressure on the garbage collector in hot paths, leading to better performance and lower memory usage. The if embedding equals null block again simulates work, just like in the task version, to ensure a fair comparison of the core asynchronous mechanism. This helper method, getEmbeddingAsTaskAsync, simulates fetching a token embedding and always returns a task float. Even if the embedding is found in the _embedding cache, lines 100 to 101, we still wrap the result in task.fromResult, cached embedding, at line 105. This task.fromResult method returns a task that is already completed with the specified result. While it's an optimization over creating a brand new task and await it still allocates a task object on the heap for each synchronous completion. This highlights the inherent cost of task for synchronous results. A heap allocation is unavoidable, which can be a performance bottleneck in high-throughput, cache-heavy scenarios. If the token is not found in our _embedding cache, lines 108 to 114, we simulate an asynchronous I/O operation. We use task run to offload this work to a thread pool thread, and task delay 10 simulates network latency or a call to an external LLM API. The key here is that this path necessarily involves asynchronous work and therefore a task allocation. The task approach is perfectly suited for truly asynchronous operations. The ValueTask optimization we'll see next only applies to the synchronous, cache hit, path, not to these genuine asynchronous operations. Here we have getEmbeddingAsValueTaskAsync, which is the star of our memory optimization. This method returns a ValueTask float. The magic happens at lines 123 to 127. If the token is found in the _embedding cache, we construct a new ValueTask float, cached embedding. Crucially, this constructor directly wraps the cached embedding value. Since ValueTask is a struct, this operation avoids any heap allocation for the ValueTask itself. The result is returned on the stack, making it incredibly efficient for synchronous completions. This is the core reason ValueTask is preferred in performance-critical scenarios where a significant portion of asynchronous operations are actually completed synchronously, like reading from a hot cache. If the token is not found in the cache, meaning we need to perform a truly asynchronous operation, like calling an external API, we still return a ValueTask float. However, at lines 132 to 137, we construct this ValueTask by wrapping a task, specifically, the task returned by task run. This means that for genuinely asynchronous operations, ValueTask still relies on an underlying task and incurs its associated heap allocation. The optimization of ValueTask is therefore conditional. It shines brightest when operations frequently complete synchronously, allowing it to avoid the task allocation. When true asynchronous work is needed, it transparently falls back to using a task internally, ensuring correctness without sacrificing the synchronous optimization. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 4, Chapter 3 of the C# and AI Masterclass ebook series and from the volume Asynchronous AI Pipelines. Async/await, parallelism, and streaming LLM responses. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.